Morning session. So the first talk this morning is by Jérémie Szeftel, so from NLS and the Laboratoire Jacques Pilions at Sorbonne University, who will talk about blow-up for supercritical defocusing NLS and compressible fluids.
Yes, well, thank you. Thank you very much. Thanks a lot for the organizers for the invitation to this conference. Okay, so there will be some repetition with the talk of Igor, so hopefully, hopefully we'll still learn something today. So everything I'm going to say is joint work with Mel, Pierre-Raphael, and Igor. And let me immediately start where Igor started. So I'm going to start with results for blow-up for NLS, and then we'll see a connection to fluids. And then I'll focus on fluids for the second part of the talk, or the third of the talk. Okay, and here let me start exactly with the same equation as Igor yesterday. So I have a defocusing NLS, and so P, my notation is that P is the power of nonlinearity, T is the dimension, and the plus sign, of course, is the important thing here. I am in the defocusing case, so in other words, if I look at the conserved energy, it is velocity. Okay, so let me briefly recall the scaling. Already saw yesterday. So there is a scale invariance for this equation with a solution. And lambda is also a solution for any strictly positive lambda if you look up this formula here. And then you can look at the action of this transformation on homogeneous Sobolev spaces. And then you find out that there is exactly one exponent which is left invariant by this transformation. So that's the critical exponent, which here is d over 2 plus 2 over p minus 1. And then you can classify your equation, as you explain, according to energy subcritical, energy critical, and energy supercritical by comparing this exponent with the natural exponent associated to the energy, which is S equal to 1. Okay, so energy subcritical case will be always the case in dimension 1 and 2. And for dimension larger or equal to 3, you will, for dimension larger or equal to 3, you will have to ask that your nonlinearity is not too strong. Then you have the energy critical case that can happen only in dimension larger or equal to 3. And the energy critical case that happens in dimension larger or equal to 3, where you strictly larger than the critical exponents. So for nonlinearities which are sufficiently strong. Okay, so we saw yesterday that in fact, if you are in the energy subcritical or critical case, then you have global existence. So let me review this briefly. So of course, the subcritical case is immediate. It's just an immediate consequence from the conservation of energy and the local Cauchy theory. So then you can extend your bound forever and you get global existence. The critical case is much more subtle. And we did quite a lot of work to be settled. So it started, well, in fact, it started earlier, but let's say the first breakthrough was by Bourgain in the radial case. And then you have the work of Oldenzakiel, Staffini, Takaoka, and Tao for the general case in dimension 3. And finally, high dimensions were done by Rickman and Vijan in dimension 4, and Vijan in dimension larger than 5. And let me also mention the alternate approach by Koenig and Merl of concentration compactness rigidity method that greatly simplified the course. Okay, and finally, as Igor explained yesterday, for various reasons, in fact, people expected global existence to hold even in the energy supercritical case. In fact, it was formalized by Jean Bourgain, but and the purpose of the talk is in particular to say that indeed, as Igor said yesterday, this conjecture is in fact not true because you have there exist finite time blow-up solutions for at least for particular ranges of D and P. Okay, so here let me first provide the first range. As I'll explain in the next slide, this is not an optimal range. It's rather due to our laziness. You will notice that here in this range of P and D, the nonlinearity always corresponds to an odd integer. That's the case where the nonlinearity is analytic. So of course that makes your life simpler, but it's absolutely non-essential. So I'll explain exactly what should be the correct range for this result in the next slide. Okay, next there is this sequence RK that will pop up many times in this talk, and we'll see exactly what it is only at the end of the talk. But for now, let me just say that it's a sequence satisfying RK strictly between 2 and some limiting value R star, which is in fact the limit of Rk as k goes to infinity. It has a special value, which of course is important, but for the purpose of following the talk, it's not important. But what I hope to explain at the end of the talk is what is exactly with this sequence Rk, and to what is special about this limiting value. Okay, so again, this Rk corresponds to blow-up speed, which means that for any such Rk, what we do is that we provide a finite convention manifold of smooth finite energy initial data in radial symmetry, such that for each of these initial data, your solution blows up in finite time at the origin. And okay, we're going to see later how the blow up proceeds. It proceeds, of course, by convergence in rescale variable to a certain profile. But for now, let me just measure the strength of the blow up in L infinity norm. So you can see here already that your solution blows up. I mean, Rk is strictly larger than 2. So you see blow up of the L infinity norm as you approach the blow up time, which necessarily means that you have finite time blow up for this solution. Okay, so let me make let me write some remarks on this result. Okay, so first of all, as we saw in Igor's talk, the heart of the proof is to make a connection with Euler, compressible Euler. Okay, so you want to use the so-called hydrodynamical formulation, and come back to it later. But so in other words, you want to rewrite your solution, which is a complex valued solution. You want to rewrite it in modulus and phase variables, and then it's known since a while that there is a connection to compressible Euler. At least most of the terms look like compressible Euler. And then there are extra terms that you will have to deal with. But the point is that it's really compressible Euler that drives the dynamic. Okay, so then what is the type of blow up? So here, this is not type 2 in the sense that, okay, actually, it's also type 2 in the sense that Igor discussed, but let me make a more trivial connection with the standard type 2. In other words, if I look at this blow up solution, if I look at the rate of blow up, the self-similar rate, which is type 1, which corresponds to Rk is equal to 2. In other words, you would have this term here, which is equal, this would be your blow up rate for a self-similar blow up. So here, you blow up faster than self-similar, since Rk is larger than 2. So this is type 2. In the sense that it's not self-similar, it's faster. And of course, that's an important feature. This is if you want to see the compressible Euler dynamics, this would be necessary to have type 2. Okay, so now let me come back on the range of parameters. So again, as I said, the range that I gave in the previous slides is completely non-sharp. If you really are willing to do a bit more effort, this is the optimal range you should get with the methods that I'm presenting here. The optimal range, in other words, the range of parameters of DNP for which Euler is dominant, which is exactly the range for which we can close the estimates, is D larger or equal to 5 and P strictly larger than 1 plus 4 over D minus 2 square root of D. Yeah, so that's the algebra. If you look at the algebra, that's what you get to make it dominant. In particular, you see that we are not saying anything about dimension 3 and 4, so this is open, and we're also not covering the full supercritical range, because let me remind you that the full energy supercritical range is P strictly larger than 1 plus 4 over D minus 2. Okay, but in any case, in principle, if you work hard enough, you get really a full range of parameters. Okay, and finally, Igor discussed the highly oscillating nature of the solution. So let me show you a little bit what is this highly oscillating nature of the solution. So if I pick, so let's fix x outside of the origin. So I'm fixing a x different from 0, and I want to, in other words, I'm outside of the blow-up point, and I want to look at the limit as t goes to the blow-up time of my solution u. And then what you see is that it actually converges to a universal profile, u star of x, and the highly oscillatory nature of the blow-up is reflected. Here you can see that the closer you get to the origin, the more oscillations you see in the phase. So it's in fact widely oscillating as you approach the origin. Okay.
Is the R sub k in the bottom?
Ah, yeah, sorry, yeah, sorry. This is our sub K. Yeah. This only works for our K. We say nothing about R different from our K. Yeah, correct. So this is our sub K. Thanks. Okay. Okay, so let me. So I want to spend still one more slide on NLS and then move to fluids. But before that, let me recall the Euler equations that we in the form that Louis likes. So let me, and we saw already in her talk and the one of Igor. So let me recall these are the barotropic compressible Euler. In other words, the pressure is a power is a function of a density, and here we actually take the special case where the pressure is the power of the density, which allows you to have a scale invariance. And sorry, is there anything I wanted to say? Well, yeah, sorry. So here for compressible fluids. Anyway, for the purpose of NLS, I will have to consider general dimension D, but here I'm just writing them dimension 3 in this slide. And let me make also a connection with the compressible Navier-Stokes, on which I'll focus after NLS. So it's just you take compressible Euler and you add viscous terms. So for compressible Navier-Stokes, they look like minus mu, Laplacian mu, minus mu prime, gradient of divergence of u, where u is the velocity. Okay, and then you have a certain range of parameters, making sure that this operator is indeed elliptic. Okay, so in the second part of the talk, I'll discuss Navier-Stokes, and in particular, again, the same story, how you can make Eulerian regime dominant so that the viscous term become negligible. But let me first come back and spend maybe one last slide on this connection to Euler. Okay. Yeah. Okay. So you begin. So first of all, the first thing you do, is very standard. So you go to the standard self-similar renormalization. So you take your solution U of NLS and you decompose it. So you go to rescale variables and unknowns. So here you go to a new unknown V, and you have a certain rescaling in front of V, which of course is dictated by the scaling. And then you rescale the space Y as X over square root of capital T minus T. And you have a rescale time variable tau, which is minus log of capital T minus little t, where capital T is the blow-up time. Okay, so this is the standard. Well, if you're familiar, you recognize the standard self-similar renormalization. If you're not familiar with it, it's a very standard. This is what you would do if you would like to prove that blow-up is type 1. Because here blow-up will be type 2, so you have to do something extra. But at least this is let's say, the starting point of most blow-up analysis. At least if you want to show rescaling by profile. Okay, and now, okay, so notice maybe one thing for those who are not used to it. While in the original variable, the blow-up time is unknown, it's a capital T, which you don't know in advance. One of the interesting feature of these rescale variables is now tau. The new blow-up time is at infinity, because as T goes to blow-up time, this goes to plus infinity. So now, instead of having a time interval which is unknown, now you are reduced to proving things semi-global results from, let's say, from tau is equal to 0 to tau is plus infinity. Okay, so again, at this stage, this is not enough, because you don't expect type 1 blow-up, you expect type 2. In fact, it's not known whether there are self-similar profiles for defocusing NLS, so you have to do something else. And this is where you have the connection to Euler. So you rewrite your, so now my new unknown is V. It's again complex valued, and I want to rewrite it using the hydrodynamical formulation. So I want to rewrite it as, so W here is my modulus and phi is the phase. And then I want to do a second rescaling. And this second rescaling now is a bit funny. It doesn't respect the scaling of the equation. In fact, that's exactly the point. I want to see Euler. And if you write things in hydrodynamical formulation, as Igor explained, you see Euler for some parts, and then there are extra terms. And in fact, if I want to see Euler, I need to kill the extra terms. So I want to do a rescaling that will just keep the Euler scaling and will kill the extra terms. So to do this, you introduce a parameter B, which will just decay exponentially in the self-similar time tau. So it particularly goes to 0 as tau goes to infinity, which is your blow-up time. And you rescale things here. And again, I claim that this scaling is such, so you go to rescaling with new unknowns. So now my unknowns, of course, since I expect to go to Euler, now I'm going to call this unknown rho. And the other one will be psi, we'll see in a minute why. And then you have a rescale space variable, which is as such. So you rescale the capital Z will be y square root of b. So here what you should understand is that this is a so-called front runnerization. In other words, if you are in self-similar variables, given that Z is equal to y square root of b, so if you think that these functions are localized functions of Z, so think of a limit, you know, I'm thinking of course, I'm thinking of converging to a stationary solution in these new variables. So if I were a stationary solution of Z, or a stationary profile of Z, then I would see in Y, what I would see in the Y variables and the self-similar variables, I would see a front. In other words, I would see something that grows like 1 over square, support is growing like 1 over square root of B. So you have a front that is invading the whole domain. Yeah. Okay, and then if you do this and you record, so now, of course, yeah, sorry. So I didn't write the equations you get in V, but it is not too important. If you plug the equations you plug this decomposition equation for V, what you obtain by taking the real imaginary part is an equation for rho and psi, which is here. So here the parameter R that was already popping up in the slide for NLS, it will pop up here. So you see this R already popping up. So this and here. So you see that R will play a role here. The parameter R, we will be able to play on this parameter R. But for now, let me just say that this funny scaling here, what it achieved is that there is only one term that doesn't scale like the rest. Okay, and this one term, what pops up in front of it is a positive power of B. Okay, and this is in particular, this was very important that in this restriction that E strictly positive is important because I want B to converge to 0 exponentially. So you can think in first approximation that what you will see at the end is that you will converge to a stationary solution. In other words, dt rho and dt psi will go to 0, at least that's the heuristic. And of course, the other thing that you can think of is that in principle, given that B goes fast to 0, this term will disappear. And in other words, in the limit, you will see just this equation with these two terms cancelled. And this, I claim, is exactly the equation of self-similar profiles for Euler. So at this stage, usually I ask people to trust me, but here you don't have to trust me. You just have to remember Igor's talk. So these are actually self-similar profiles to Euler. Again, if this term vanishes in this one also, provided, of course, that you write the sorry. So here I have a conflict of notation. So this U is not this U. This U is the U of Euler. Okay, I don't have enough letters apparently, but so if you write the U of Euler as gradient of psi, in other words, you are in the so-called irrotational case, which of course is the case here because we are in radial symmetry, so you're always irrotational. Then if you do this, it's actually quite easy to see that these are self-similar profiles to Euler, provided you realize that this equation is the so-called Bernoulli equation. In other words, you integrate it once the equation for you. Okay. Okay. So Igor suggested that I'll be more technical, but I'm not sure I want to be too technical here. So let me just tell you slightly more before moving to something else on how you deal exactly with the fact that you have an extra term here. Okay. So the goal is pretty clear, as long as you trust me that this looks like self-similar Euler, provided you remove that term. The goal is I'm going to decompose rho and psi. I'm going to decompose rho. No, maybe it's not good. Okay, let me write in the middle then. I'm going to write rho, let's say, is equal to some Euler profile. So let me write rho p plus some remainder. I don't know, check. And I'm going to write psi is equal to psi p plus psi check. And of course, the goal, so rho check is of course a self-similar. So rho check is a self-similar solution to Euler. Like there is a slight, I mean, you have to modify actually this profile because, as we'll see, it decays very slowly at infinity. So you have to modify it. But let me not get into that. Just let me pretend I plug the Euler profile here. And then, of course, your goal is to control the remainder. You want to show that rho check and psi check, at least up to a finite number of modes, converges to 0 plus 2 goes to infinity, the self-similar time goes to infinity. But of course, when you plug this decomposition, given that your profile is not an exact solution, what you get an extra term here, which would be like b square Laplace of rho p, simply because the Euler profile does not have this, does not satisfy this extra term. Okay, so you have to deal with this b square Laplace term, which you could think of course, given that b goes to 0, you should think of it as a forcing right-hand side. You should throw it on the right-hand side and just live with it. And as you well know, you cannot always do this because at top order energy, you will lose derivative. Okay, so the goal is the following. For low derivatives, as usual, you're going to prove decay estimates. So for low derivatives, in fact, just throw it on the right-hand side, you linearize the equation, you get some linear decay estimates, which I'll talk a little bit later about. And you really use it as a forcing term and use the fact that it decays exponentially fast. And then at top order energy, on the other hand, of course, you have to rely on the fact there is an underlying energy for this problem. So you will use this energy to not lose derivatives. So this time you will not throw it on the right-hand side. You will really use the sign of this term. And then, of course, there is the intermediate region. What do you do between top order derivatives and low order derivatives? And the constraint is that, as it's standard, or at least usual, for low order derivatives, you get localized norms. So you have weighted norms that localizes near the profile, while for top order energy, if I want to use the energy for this problem, it's unweighted. So then you have a descent scheme to go from low derivative with weights to high derivative without weights. I have a descent scheme where you descend in your weight until you can transition from the weight of needed for the T estimates to 0 weight for top order energy. Okay, maybe let me not say more about it. And okay, so from now on, I will switch actually to compressible fluids. Okay, so let me recall the main feature of the proof. So as Igor said, the main thing, the main toy or the main magical tool we have is the fact that there is something very special about Euler, at least compared to the usual equations that we know, at least that I know of. Okay, and this special thing has to do with the fact that the scale invariance has two parameters. There is, of course, the first usual parameter, the lambda. So if U and rho are solution to Euler, then U lambda, rho lambda are again solution to Euler. But as you can see, there is a free parameter R in the powers of lambda here. In other words, for any values of R, this respects this is again a solution to Euler. Okay, and this, of course, this R is directly related to this sequence arcade that I was showing. Okay, so we'll see that this is your main tool. This is the main game you want to play. You want to play with this free parameter and say that for some very special value of that parameter, you can actually produce smooth self-similar profiles for compressible Euler. Okay, but for now, let me just remember that this is a free parameter. And then, of course, since I'm going to focus on compressible Navier-Stokes, let me also mention that Navier-Stokes has a scaling, but now you're in a more familiar territory of a one-parameter scaling. So the scaling, in fact, of course, the scaling of Navier-Stokes coincide with the Euler one for a particular case, and here the particular value is R is equal to 2 gamma over gamma plus 1. Okay, okay, so now so now I'm going to review a little bit some results for Euler and Navier-Stokes before I can quote the results. So let me start by reviewing what was known for blow-up solutions, finite time blow-up for compressible Navier-Stokes. Okay, so first of all, you have the result of Xin. So first of all, the only thing that was known are variable type computations. In other words, you produce blow-up by an indirect argument that tells you that there are blow-up solutions. So there is the result of Xin. So this is a surprisingly strong result. It tells you that if you start in the compactly supported case, then you get blow-up for any data in any dimension. Okay, so there is something very special about this compactly supported data. We saw in the talk of Juhi that they give you some trouble where the density vanishes. But in any case, if you're compactly supported for free, you know that they all blow up. Okay, so we will not be in this case precisely because of well, first of all, in fact, the main thing is that we want to apply to NLS. So if you want the hydrodynamical formulation to make sense, you don't want rho to vanish. But in any case, the vanishing of rho creates some extra difficulties. So here we really want to be in the non-vanishing case. So more relevant, what I'm going to say is the result of Rosanova, where she can prove blow-up in any dimension larger or equal to 3 for this time, not for all data, it's only for some data, but it is an open set of data. Interestingly, none of these data apply to our result because necessarily some quantity has to be non-zero and this quantity vanishes for any radial solution. So it only applies to non-radial solutions. So there's a empty intersection between the result and ours. Okay, and of course, as in any VLTAP result, it doesn't give you any description of blow-up dynamic. It doesn't tell you what is time of blow-up or speed of blow-up or profile. So it's just an information that something goes wrong. Okay, and finally, there is one last result that will be relevant, is the fact that global existence is known, in fact, in the case where rho is close to 1 and u is close to 0. In other words, if you're near what is called the constant density regime, then global existence, in fact, there are lots of results around this thing. I mean, in other words, if you are suitably in a suitable norm, if you are close to 1, 0, then you have global existence. Okay, so now let me review some works on compressible error. So here, I don't know, we say that I would say that I'm walking on eggs in French because there are lots of experts, so I'm sure I'm going to say something completely stupid. So please, if I'm saying something stupid, tell me. Okay, so for compressible Euler, you have again, you have a variable computation. So there is the result of Segeris that tells you that in fact there are lots of solutions blowing up. But then we know much more. In fact, there are lots of refined results. So the first thing that was achieved is that shock forms in radial symmetry. I think this is due to Fritz John. And formation of shock in the general case is due to Serge Alinac. And then in the wake of the breakthrough work by Christou, there are lots of work on stable shock formation in the general case. In other words, without symmetry, but stable shock formation, in other words, you really exhibit an open set of data leading to blow up. So there is the result of Christou, and then there are results by Miao and Christou, Miao and Yu. There are lots of important results by Jared and Jonathan that we'll hear again this week, Jonathan later in the week. And then there are work by Vikol, Buchmaster, Score and Rivas. So there is a sequence of work, and I hope I didn't forget anything here. Okay, so the main thing is that all these results are always shock formation, and in fact, this is the physically relevant regime. So this is exactly what you want to do for Euler. You want to prove formation of shock for compressible Euler, but here, for application to compressible Navier-Stokes, in fact, we'll have to depart from this type of mechanism simply because they are usually derived in the small data near constant density regime, and that's exactly the regime for which Navier-Stokes cannot blow up. So you cannot expect that this will be the leading term in your dynamic for compressible Navier-Stokes. Okay, so maybe let me spend one slide explaining what is the strategy for compressible Navier-Stokes, even though on the NLS, I think this slide is pretty clear. You want to mimic exactly what you did. So the first thing is that your blow-up mechanism is such that you want Euler to become dominant, which means that you want the extra term, which here are the dissipative term, sorry. You want your dissipative term to become negligible at the blow-up time compared to the other terms. Of course, they will also blow up, but you want them to blow up slower. Okay, then of course, so as I said in the previous slide, you cannot rely on shock formation simply because you don't expect this blow-up regime to hold in the Navier-Stokes case. So you want to rely on another blow-up mechanism for Euler. And here I should say that while we'll also get blow-up for Euler, I should mention that, of course, this is not the physically relevant regime. We'll get another regime which is not so interesting for Euler, but which will allow us to produce a blowing up solution for Navier-Stokes. And the magic trick is exactly the same as NLS. You want to use the 2-parameter scaling. And here the game is that you want to choose the 3-parameter R such that Euler is dominant, which means that you want the scaling, this R to be strictly stronger and the corresponding scaling for Navier-Stokes, which was 2 gamma over gamma plus 1. Of course, if you do this, you immediately see this is exactly what we produce in rescaled variables. Now, if I go to the self-similar variables exactly as I did for NLS, I don't even have to do an extra massage. I will immediately see, because I don't respect the scaling of Navier-Stokes, I will immediately see this P square in front of the dissipative term. So it will be exactly the same mechanism for NLS, except I don't have to do an extra massage of the equation, I immediately get it in self-similar variables. Okay, and of course, the main ingredient here, which I still didn't talk about, is that everything I said so far always assumes that that we are able to construct self-similar profiles for compressible Euler. In a range, of course, for a range of R for which Euler is dominant. Okay, so maybe let me now code the result on compressible Navier-Stokes. So again, this is joint work with Franklin, Pierre-Raphael, and Igor. Okay, here let me maybe explain the notation because I'm going to use it. So in order to make things consistent between Navier-Stokes and NLS, we always have this parameter R, which scales to the inverse power of the nonlinearity. And here I'm going to assume that L is different from 3, so I'm going to explain later why you have to assume this. This is a special case. This is a degenerate case, and in fact, it's a physically relevant case, but I'll explain later. For now, let me mention that for Navier-Stokes, you have the further restriction that L is strictly larger than square root of 3, while for Euler, any strictly positive L works. Okay, so of course, this slide looks very much like the NLS. Again, you see your favorite sequence of RK, which will only be explained at the end, such that this RK converges in the limit to a special value. And then for any of these blow-up speed RK, you will have again a finite codimension manifold of smooth spherically symmetric data that blow up in finite time at the origin. And let me also tell you how they blow up. This is where you see that they blow up. This is what is called an implosion. It's not a shock formation, it's an implosion, simply because the L infinite term of the density blows up itself, not just the first order derivatives. Yeah, so it's not on the slide. So RK here is strictly larger than 1, so this is you have blow up of the L infinity. Okay, so again, some couple of remarks. So first of all, what is this restriction L strictly larger than square root of 3? So this is exactly as for NLS. This is a sharp restriction. You need this to make sure that the Eulerian regime becomes dominant. So this is exactly this. I mean, if you write it carefully, you will see that this is exactly necessary if you want the Euler to dominate. So if you want to be able to choose this RK to be strictly larger than the Navier-Stokes scaling. Second, the results are uniform with respect to viscosity. So if you are, in other words, if you are in the range where you can produce blow-up solutions both for Navier-Stokes and Euler, then you get blow-up for the same initial data, and in fact, it's uniform. The proof is uniform in viscosity. You can pass from Navier-Stokes to Euler in the limit, and you will get the blow-up solutions for Euler from the world of Navier-Stokes. So this remark should look familiar. Again, for Euler, of course, it has to be type 1 because by definition, we are relying on a self-similar profile. But for Navier-Stokes, it has to be type 2 because we are not respecting the scaling of Navier-Stokes. Okay, so this is type 2 exactly as for NLS. And as we have seen in the previous slide, rho and U blow up in L infinity norm. So this is an implosion. This is not shock formation. And finally, if you are in the particular range between 3/2 and 1 + 2 over square root of 3, then it turns out that the solution coexists with the weak solution constructed by Pierre Williams for compressible Navier-Stokes. So if you take the initial data that corresponds to our finite time blow-up solutions, in the strong sense, as strong solutions, they blow up in finite time, and as weak solutions, they exist globally. Okay. Okay, so that finishes what I wanted to say on compressible Navier-Stokes, and then let me finish the talk with about the main ingredients in all these results, which is the existence of these profiles for self-similar profiles for compressible Euler. Okay, so here I rewrote the equation of self-similar profiles for Euler. I think we saw it in the talk of Igor. In any case, if we didn't see them, trust me that this is what you're looking for. You rescale, you go to self-similar variables, you look for stationary solution in the self-similar variables, and this is the equation you're trying to solve. So here, unlike what we will discuss for NLS, in this case, this is not an elliptic problem, rather looks like a nonlinear transport. Okay, so this is again joint work. So you take, so here, I'm going to take the dimension to be larger or equal to 2. Obviously, for Euler, it's not, dimension larger or equal to 4 doesn't really make any sense, but recall that I want to apply it to NLS. So in that sense, it's useful in that sense. Okay, so the result is that for almost any L, there exists a discrete sequence. So this is our favorite sequence RK. So this is exactly when we will exactly understand what is this RK, which converges to a limiting value R star, such that for any R is equal to RK, you get a smooth, and smooth is the important word here, strictly symmetric self-similar profile of compressible Euler, in other words, the solution to this problem. And for reasons having to do with the application to NLS, I absolutely insist on having rho and u converging both to 0 at infinity. It's not probably not so important for compressible Navier-Stokes, but certainly it's important for compressible, for NLS, for linear Schrödinger. And of course, by the way, you want we want them to converge to 0, but you want rho to be strictly positive everywhere. Okay, so let me in the probably about 15 minutes, I guess. Let me discuss a little bit how you construct this profile. Okay, so first, let me do some remarks. I'm not familiar with my slides. So first, you want first remark exactly as Julie mentioned in her case, you want your self-similar profile are going to decay slowly. In particular, they absolutely don't have finite energy. This is a natural feature of supercriticality. So they are not finite energy, neither for NLS nor for Navier-Stokes nor for Euler. But sorry, Euler, I don't remember. Certainly not for NLS and Navier-Stokes. So what you want to do, obviously, is you want to dump them. In other words, you want to decide that they are relevant for a very large region, and then very far away, you need to decide exactly when you want to dump them. In other words, you're going to ask them to have extra decay very far away. So this profile will be relevant in a very large compact region, and at some point you want to say that they are not relevant anymore because they don't decay enough. Okay, also, what happens for R different from this special value RK? So as Igor mentioned, you still have self-linear profile, and in fact, they are still regular. And in fact, I should mention that they are, as soon as you approach this limit R star, they are more and more regular. They tend to say infinity. There are more and more derivatives. So what is wrong with these profiles? What is wrong is that you want to do, for decay estimates, you want to look at the linearized operator and you want to extract decay estimates. And the way you do it is that you're going to prove that your linearized operator decomposes as an aggressive operator plus a compact perturbation. So the compact perturbation has to do with the finite number of modes. So it's the finite codimension. So let me forget about it. The main estimate is to prove that the main part of your linear operator is accretive. And to do this, you need to show that there is at some level a positive quadratic form. And the way you exhibit positivity of this quadratic form is by commuting your equation by many, many derivatives. And if you do it sufficiently many times, then it turns out that for a certain value, you actually get a positive quadratic form. The problem is that the number of times you have to commute is actually larger than the finite regularity that you get for R different from RK. Okay, it's quite frustrating. It's only about one derivative more, but okay, that's it. So in other words, if R is different from RK, we cannot carry out a linear analysis and then everything collapses. That's why it's really crucial that you get smooth profiles. Okay, another thing I should say is that the profiles we are constructing here are highly non-generic. These are very, very fine-tuned solutions. If you look at a self-similar profile in general, you will always see a shock. The generic behavior is a shock. These are the solutions that Igor discussed that were constructed by Gödel and Sedov. So the generic behavior is to have a shock. In other words, you're going to cross the sonic line and you will experience a problem there. And if you want not to have a problem when you cross the sonic line, you have to fine-tune things. Okay, there is this case, okay, in dimension 3 it was L equal to 3, in general it's L equal to D. There is this special case that is never covered by our result. So here, I should mention that in dimension 3, it's actually an important case. It corresponds to monoatomic gases, so it's a physically relevant case. This case is just generated in our analysis, and I'll explain why, but certainly it's not possible. Okay, so that's what I wanted to say on comments on the proof. So let me make some connections with later work. So first, there is this numerical work by Oshiobiashi where he actually could fine-tune numerically the solution to see these smooth solutions, these profiles that we're constructing. And he actually could observe that there are indeed unstable modes that do not come from the scaling. So in other words, the finite codimension feature of the result is essential. You don't expect a stable blow-up regime here. Let me also mention an extension of our result by Bookmaster Candelabra and Gomez Serrano to cover the full range. And let me, of course, mention the connection with what Julie said yesterday from her joint work with Yangu and Mahia Hachik. And I think there's also, sorry, there's one paper also with Schreiker on these self-similar solutions for Einstein, Euler, and Euler-Poisson. Okay, so let me finish by explaining a little bit. I want to explain this sequence. Okay, I want to tell you a little bit more about this sequence. Okay, so let me start again with the equations of self-similar profiles for Euler. Let me immediately recast it in a different form. I'm not going to tell you how you recast it. Just trust me that if you massage the equations, you can actually reduce these equations to a much simpler. Of course, it's in radial symmetry, right? In radial symmetry, and reduce this to something much nicer, which is just a 2x2 autonomous ODE system. Okay, so you have now your rho and u are two new unknowns. Let me not say exactly how they are connected, but you have two unknowns, W and sigma, and then your ODE system is that W prime is minus delta 1 over delta, sigma prime is minus delta 2 over delta, and delta, delta 1, delta 2 are explicit polynomials in omega and sigma. So you have a 2x2 autonomous system. Okay, so yesterday, Julie told us that it's not so easy to deal with a 2x2 non-autonomous system. And here it's even autonomous, and yet it's still not easy. And of course, what is difficult in all these problems, this was exactly the same for Juhi. The problem is that you have the denominator can vanish, delta can be 0. And in fact, delta being 0 exactly corresponds in these variables to the sonic line. So is where you're going to cross the sonic line, and as we're going to see, unfortunately, you do have to cross the sonic line. Okay, in any case, clearly, given the nature of your system, it's very important if you want to understand equilibrium or the sonic line, you need to look at the location of the roots of these polynomials. So let me draw the phase portrait for you. So here on this picture, the zeros, the sonic lines, in other words, the zeros of delta in black. So there are these two straight lines here. Then the zeros of delta 2, which is the denominator of sigma prime, are the green curves here. And finally, the red curves are the zeros of delta 1, in other words, the denominator of omega prime. Okay, so what is the goal here? Of course, I mean, I changed my variables and didn't really tell you how I changed them, but trust me that first of all, you want a radial solution at the origin, and due to the change of variable, the origin now is at infinity. So you want to start at this P6 point, and that will mean that you are radial at the origin. And then you want to converge to 0 at infinity, and the point that corresponds to 0 at infinity now is at the origin, it's this P4 point. Okay, so in other words, if I want a radial solution that converges to 0 at infinity, then I want to connect P6, P4, and I want to connect it in a smooth way. And of course, the bad news is that when I go from P6 to P4, I have to cross the sonic line. Okay, so this is what I was saying about generic solutions. Generically, you will cross the sonic line and get a shock simply because your derivative has delta on the denominator. But of course, what you can do, on the other hand, is you can try to cross it where delta 1 and delta 2 also vanish. I think this was exactly the game that we played yesterday. So you want to cross at a point where delta 1 and delta 2 also vanish, so that at least you can have a chance to be smooth. It doesn't mean you will be smooth, but at least you could hope for it. Which means that you're looking at triple points, which are the triple zeros, the zeros both of that coincides with the zero of delta 1, delta 2, and delta. And in fact, on the picture, you can see there are two such points. I have two triple points. I have the P2 point here, which exactly coincides with the intersection of the red, the green, and the black curve. And I also have the P3 point. So in other words, I want to go from P6 to P4 by going either through P2 or P3. However, in view of the signs of this delta, delta 1, and delta 2, it turns out that a simple phase portrait analysis tells you that you don't have the choice. You really have to go through P2. P3 is excluded. If you want to connect P6 to P4, there is a problem. You cannot go through P3, so you have to go through P2. Okay, so maybe now I can talk about the special points. Okay, so first, this is a summary. The curve must connect P6 to P4 while staying smooth. And to have a chance to be smooth, you want to go through P2. In other words, if you don't go through P2, you just get the good NLS set of solution, which have a sharp by design. Okay, so, sorry. What is this? Well, in fact, let me maybe show it immediately. So this is the curve you want. I want a curve starting at P6, going through P2 in a smooth way. And of course, this would be the crucial point. This would be a crucial difficulty. And then I'll go to the P. Okay, so now the limit, what is this special limit R is equal to R star? That seems to be an important role. This limit R is equal to R star corresponds to the degenerate case where P5 is equal to P2. In other words, I did not yet talk about P5. P5 is an equilibrium in your problem. It has both denominators 0, but outside the sonic line. So this is an equilibrium. Okay, in particular, I want to avoid by point because if I go to P5, then I don't go to P4. But in any case, what you will obtain is a result where P5 goes to P2. In other words, this region that we usually call the eye, because it looks like an eye between the green and the red curve, this is going to crunch to one point in the limit. So you are actually achieving the construction when this eye is very small. So this is your small parameter. The small parameter in this problem is the distance between P5 and P2. This is what you want to exploit. And finally, what is this degenerate case L equal to D? So the degenerate case corresponds to the triple point. So this is the case which is excluded by analysis. We cannot deal with the very degenerate case where both the 3 points crunch. In other words, where P3 is equal to P5 is equal to P2. That's L equal to D. The case we are not able to deal. Okay, so finally, let me finish with a last slide on explaining a little bit how the proof goes. So again, I want to achieve this curve that goes from P6 to P4. And the main thing is to go through P2 in a smooth way. And this is where you will have to fine-tune the parameter R. Okay, so first, so this is where you're very happy to have a phase portrait. Just by phase portrait analysis, there are parts of the analysis which are very, very simple. Essentially, just looking at a phase portrait and doing some, maybe looking at the asymptotic as you approach P4 and P6. So the first thing is that if you look at the signs on your phase portrait, you will realize that any curve that starts here will automatically go to P2 on the right and go to P4 on the left. You are trapped. There's nothing else you can do. So any curve that are between P5 and that cross the red curve between P4, or that start, if you want, on the red curve between P5 and P2, must go to P4 on one side and must reach P2 in finite time. Okay, so that gives you a lot, at least on the left of P2, you have lots of good candidates, and you can hope that one of them will do the job. On the right, you're a bit less lucky. In other words, on the right, there is only, on the right of P2, there is only one curve that you like, because it turns out that there is a unique smooth curve that connects P2 to P6. So here, on the right of P2, in fact, this is this curve. There is a unique curve that goes from P6 to P2, and it ends up in P2 in finite time, and it's smooth outside of P2. Okay, so far you have produced, in fact, so far I can already produce this solution which has finite regularity. You connect this unique curve here to any of the curve on the other side, and I claim that you already have produced a self-similar solution with finite regularity. And now you want a smooth curve. Sorry. That's my lesson. Sorry. Okay, so then third information, there is a unique smooth curve through P2. Already, this is not from the phase portrait. You have to work a little bit more. But it turns out that through P2, there is a unique smooth curve. So what you should understand is that in this picture, there are infinitely many curves. Any curve starting here, or any curve starting crossing red here, they all end up at P2. So you have infinitely many curves and then you get at P2. It turns out there's a unique one which is smooth. Okay, so then the game is pretty obvious. You want to adjust the value of R such that the three curves coincide. Okay, so maybe let me say one word on how you do it. So what you will do, you will produce an interval. So let's say I'm going to produce an interval RK minus RK plus, where here, of course, RK minus and RK plus both converge to this limiting value R star as K goes to infinity. And you want to produce your special value Rk, of course, in this interval. So what is special about this interval? What you can prove is that if you are and of course you have infinitely many of them because you have as many as k. So, so if you are within this interval, what's happening is that on the left, sorry, let me come here. On the left, any member of this, if you take R in this interval, then the smooth curve will always cross red, which means that you already done half of the job. The smooth curve will always cross the red. So the smooth curve through P2 could either, in fact, it never ends up at P5, but it could either exit the region by crossing red or by crossing green. Sorry, I'm Daltonian or something. So crossing green, sorry, or crossing red. And what you want, of course, is crossing red. So you can produce intervals where it always crosses green or intervals where it always crosses red. Okay, and of course, the ones I like are the one where it crosses red. So in this interval, you ensure that the curve, the smooth curve at P2 ends up at P4. So you already did half of the job. The other half is to show that it will coincide with the curve going to P6 on the other side. So how you do this, then what the remaining thing is actually, so in fact, this is the hard part. The hard part is to have full control of the smooth solution on a full interval. This is the difficult part. The other side is actually easier because on the other side, you just have to work at the boundary of the intervals where actually things are easier to control. So I claim that if you are on one of the boundary, the smooth curve will exit on the right by green. And if you are on the other part of the, very close to the other part of the boundary interval, you will exit red. So that by the mean value theorem, there has to be at least one value k where exactly coincide with the curve going to P6, and then that will be your smooth solution. Okay, I'll stop here. Thank you very much.